talked about last time, what we got, started to get our heads around. So we learned the definition of Hess's law, overall enthalpy change, independent of the path taken. We spent some time thinking about that. A couple of nice examples on there where A is turning to B, and you've got this on the left hand side, you've got this pathway A turning to X, then to Y, then to B. So you can work out the enthalpy change of the reaction A going to B by looking at the energy changes of the other processes. And we've got a slightly different example on the right hand side there. That one we've got A turning into C turning into B, and you can work out from that what the energy changes are by looking at, by simply adding together those values. So clockwise equal to anti-clockwise, there we go, where we've got on that right hand side example, you've got A1 is equal to delta H2 plus delta H3. And the reason you might do that is because there are reactions where you can't measure the enthalpy change directly, and so you measure enthalpy changes you can do yourself. And we did a little practical of that, which we'll come back to in due course. There's a few things in this topic I know we need to come back to. Right, so that's what we've done so far. I'll give you another slightly different general example. Then we're going to go through some worked examples from the page. I stupidly didn't bring a calculator, so when we come to do some sums, I'm going to ask you to tap the numbers in for me as we go along. But just another sort of general example. So the one I showed you a minute ago is A turning into B. You don't need to write this out again, but going to C and then up to B. Delta H1, delta H2. The numbers of delta H is just decided to call it that, completely arbitrary. I could call them delta H X, Y and Z. Doesn't matter what they're called. We just understand that in this example, the clockwise arrows, which is delta H1, equal to the energy changes associated with the anti-clockwise arrows, delta H2 and 3. Another example could be A going to B. This is like we did in the practical, you'll see in due course. We could turn A into C and B into C. And I'm going to call this delta HX, delta HY, and delta HZ. And hopefully you can see again that clockwise equals anti-clockwise, but the clockwise arrows there are this one and this one. So delta HX and delta HZ are clockwise, delta HX and delta HZ are clockwise, and delta HY is anti-clockwise. So if I wanted to work out delta HX, I'll have to do a little tiny bit of year 7 algebra and say that delta HX is equal to delta HY take away delta HZ. So you can either do it algebraically like I've just done there, very simple algebra that, isn't it? One thing take away the other and all that. Or you can look at the Hess cycle and work it out from the cycle as well. So if I want to get from A to B, I go from A to C and then the reverse of C to B. You see? So it's a take away. So if my path from A to B involves going against one of the arrows, I take away the enthalpy change associated with the arrow, right? But we'll see that in a number of examples now. So that's what we're going to do. We're going to work through, for the sake of the people not here, working through examples from this sheet here, which is called Hess Cycles worksheet. I'll make sure that's uploaded onto the classroom as well. So the first one of them then is to calculate the enthalpy change of hydrogenation of benzene to cyclohexane. You're given some information about that we need. So C6H6 liquid reacting with hydrogen gas going to C6H12 cyclohexane. And that's a liquid, and so that's delta HR for that reaction. So remember the definition of delta HR is the enthalpy change basically as written on the balanced equation with everything in the standard states and standard conditions. So enthalpy changes of reaction as written. But you're told here the enthalpy changes of combustion of benzene and hydrogen and cyclohexane. So we know that if I burn benzene, we should be able to work out what products we get. If we burn a hydrocarbon, we should know that we get carbon dioxide and water produced, and that would be also carbon dioxide if I burn cyclohexane. And if I burn hydrogen, I get water. So in other words, the products of combustion of the reactants are the same as the products of combustion of the products. Okay. And so I've drawn downward arrows because we learned those definitions really carefully, didn't we? Of the enthalpy change of combustion, which is the enthalpy change when 1 mole of a substance is burnt fully in oxygen to give products, right? But these reactions at the moment aren't balanced, are they? So we're first of all going to get that right. The top reaction's balanced, the top equation's balanced, but to balance the bottom, to balance these, I've got to have 6 moles of carbon dioxide produced, which is true for both of those. And I've got to have 3 moles, I'm sorry, that's wrong. It's 6 moles of water produced, right? Because I've got 12 hydrogens on the left and the right. So I'm going to generate 6 moles of water because 12 hydrogen atoms. There is something missing from this Hess cycle, isn't there? Which is that I haven't added the oxygen that we need to combust stuff. So we really should add that, and you can see it in different ways depending on what book you look in or which video you watch. Sometimes people put the oxygen on the balanced equation, which I quite like. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 11, 12. Add 6 is 18, and then so we need 9 lots of oxygen there and 9 lots of oxygen there. Note that in that top reaction, the fact that 9 moles of oxygen turn into 9 moles of oxygen is irrelevant for that enthalpy change because that is no change. Okay. This arrow on the left hand side then, I'm going to give you a sec, I'm just going to pause the video, give you a chance to copy this up. Alright, so that enthalpy change there, going from benzene to carbon dioxide and water, is given in the question here. So the enthalpy change of combustion of benzene in here. So we're going to add that to this arrow. So delta HC standard for C6 H6. Notice it's essential that the arrow goes in the downward direction for that one because it's combustion of benzene. But we've got something else to add to that arrow as well, because that arrow also includes the conversion of the hydrogen into water, oxidation of the hydrogen to water using oxygen. That one we've got to think a little bit harder, because the enthalpy change of combustion is the enthalpy change when 1 mole of hydrogen burns, but we're actually burning 3 moles of hydrogen, so we've got to do 3 times the enthalpy change of combustion of H2. Okay. And over here, this is just burning 1 mole of cyclohexane, which is given in the question. Okay. So that's what you can do there. You can add those values. Now, some people just like to put the values directly on the Hess cycle. I quite like that too. So why don't we do that? So hopefully you've got room to squeeze them in. If you haven't, you can write it underneath. The enthalpy change of combustion of benzene is minus 3,267, and this is equal to 3 lots of minus 286. Why have I multiplied that by 3? Tell the person next to you, why have I multiplied that 286 by 3? Right? Yeah, good, you all said the right thing there. When some of you get this wrong in your test, when I test you on this, the thing you'll get wrong is you'll forget to multiply by the coefficient, so don't do that because that's the common mistake. And over here, this one is minus 3920, and the next question I've got for you to check understanding is, why is it that I've got a downwards arrow there rather than an upwards arrow? Tell the people next to you, near you. Happy? Yeah. All right. So then it's easy. Then it's year 7 maths, right? It's clockwise equals anti-clockwise. So you're going to give me a thumbs up if you think this arrow is clockwise. If you thumbs down if you think it's anti-clockwise. Thumbs up is clockwise. Hurrah. What about this one? Is this clockwise or anti-clockwise? Yeah. There's some funny clocks in your house. And this one is anti-clockwise or clockwise? Good, you will give me a thumbs down. That's good. Right, so well done. So we've got the idea. So we just write down the clockwise arrows, which are delta HR standard. The thing I'm trying to work out is equal. Whoops. Clockwise 1. So add minus 3920. I like doing add minus so that you can see everything that's going on. I'm adding together the clockwise side, so I even write it underneath if you like, clockwise equal to anti-clockwise. The anti-clockwise ones are minus 3267, but I've also got 3 lots of minus 286 there. That's the anti-clockwise sides. Notice this term, well, this arrow, if you like, is loaded with both of the numbers from that arrow, anti-clock. And then it's just a case of plugging the numbers in, and you'll find that delta H of R is equal to minus 3267. Hoping that someone's tapping around their calculator right now. Add 3 lots of minus 286, and then it's take away minus 3920, so I'm just going to write plus 3920. Hopefully it'll give me someone will give me a value in kilojoules per mole for that, please. Can someone please check that? So I've got 2 versions of that, and we get at least one of them. Hopefully that's right. Yeah, same. So we're getting minus 205. The method's certainly right, even if we slip up on the numbers there. Now, I'm also going to show you a shortcut to this, which you need to know really to save you an awful lot of time. But I've shown you where it comes from, which is delta H for a reaction, and this is an equation you need to know and learn. Stick on a flashcard or something. The delta H for reaction is equal to. Does this look familiar so far? We did one of these for formation, didn't we? And I'll show you where that comes from in a minute. But this is slightly different. So the sum of the enthalpy changes of combustion, and look here, it's the products. Let's get the right way around. Reactants take away the products. There we go. So that is what we've just worked out with the Hess cycle. That equation that you're supposed to know, which is the easy way to this. If you're really struggling with these Hess cycles, which some of you will probably, if you can learn that, you'll get probably all the marks in your IB anyway. But I want to teach you where it comes from. Hopefully I've done that clear enough for you. Right, I'm just going to move on. You can come back to that, or if you need any help, I'll deal with it as we go. Any burning questions on that before I do example 2? Right, so example 2 then. We're going to look at reaction. Again, this is a thermal decomposition, so we can't measure this directly. So it's lithium carbonate goes to lithium oxide plus carbon dioxide. And we're told in the question the enthalpy changes of formation. And we all know the definition of that, don't we?
Formation.
Enthalpy change when?
When 1 mole of substance.
You haven't learnt it yet, right? You haven't learnt it yet. You've got to learn it. People are looking away from you. Everyone's got their eyes to their knees. No. No. Formation. Yeah, that is it. Enthalpy change when?
When 1 mole of substance is
Formed from. How many of you know it? How many of you actually memorised it yet? I don't believe it's just 2 of you. I don't believe that. I've asked you to go away and learn this. I've asked you to make a flashcard on it. I'm expecting you to be figuring this stuff out and learning it. So disappointing, but we'll get there. It's the enthalpy change when 1 mole of a substance forms from its elements with all reactants and products at the standard states and under standard conditions. You are all capable of learning definitions. You need to learn them. Okay. Now the elements that form lithium carbonate are lithium and carbon and oxygen. And funnily enough, given it's a balanced equation, they're also the same elements which you need to make lithium oxide and carbon dioxide, right? But to balance this up, how many lithiums do I need down there? How many carbons do I need down there? And how many oxygens do I need down there? Someone? Yeah, 1.5. And we should put state symbols really for being good. Let's get those up there as well. You cannot do this most difficult skill, tricky skill, without learning the definition. So if you think that's going to work, yeah, good luck would be my advice, my comment. Now I'm drawing upwards arrows this time for both of these because they're both enthalpy changes of formation. If one was combustion and one was formation, one would be up and one would be down. You need to know which way the arrows go because the definition of enthalpy change of formation is when 1 mole of a substance forms from its elements. So this arrow here is the enthalpy change of formation of lithium carbonate, and this here is the enthalpy change of formation of lithium oxide, and the enthalpy change of formation of carbon dioxide. That's what those arrows are. I don't need to double anything up or triple anything because there's only 1 mole of each of them. The coefficient is 1 in each case. That's it. All we've got to do then is identify what's clockwise and what's anti-clockwise. And I think we can work that out. So this is the enthalpy change I'm interested in. And so the clockwise arrows, I'm just going to do it simple. I'm just going to call them A and B and C this time. Hopefully we can see that A and B are clockwise and C is anti-clockwise. And I therefore need to show what the enthalpy change for B is. B is C, take away A. Okay, just use simple algebra again. Or we can look at the Hess cycle and see to go from lithium carbonate to lithium oxide, I've got to go against A, so minus A, with C, plus C. So that all works nicely. So we plug the numbers in. So the enthalpy change of the reaction that I've written down here, delta HR, is equal to C, which is in the question up here, enthalpy change of formation of carbon dioxide and lithium oxide, take away A, which is the enthalpy change of formation of lithium carbonate. And I'd be grateful if someone could just tap those numbers into a calculator for me, or to a couple of people, so I've got to double check. Plus 224. So with enthalpy changes, we always give the sign plus 224. Did you say? And can someone just confirm that, please, to get the same number? I've got a few nods from the room. Thank you very much. 224 kilojoules per mole for that one. And you might remember something I showed you last time, was the enthalpy changes of formation is defined, well, it can be worked out using the shorthand method of the, sorry, beg your pardon, that's a mistake. Delta H for a reaction is equal to the sum of the enthalpy changes of formation of the products, take away the sum of the enthalpy changes of formation of the reactants. Okay, and that is exactly what this is up here. So it's the sum of all of the products, lithium oxide and carbon dioxide, take away the enthalpy change of formation of the lithium carbonate. So all we've done is we've shown how this, or where this comes from. So I want you, absolutely, you must know this and be able to use it. I also would like you to know where it comes from. The previous question one was all combustion, this one's formation. You can get questions where they're a mixture, one's combustion, one's formation, and then you need to think about, this is why you need to teach you properly how to do it. You can't always rely on this kind of shorthand method, because you might get a mixed set of information there. So teaching you proper Hess cycles is good. Shall I leave you to try to do one more by yourself, and if I work quietly working through it, I'll do question 3 with you. Can you try to do question 3 and question 4 by yourself? But I'm going to do it up here, so if you're stuck you can look up, try to do it without my assistance. I'm going to pause the video so I don't end up having lots of empty time. So for the sake of the video, question 3's answer is there. You can check it, make sure you got it right. And I'll do question 4 in a sec. Can you just check your answers to question 4, which is there? And I haven't done question 5 myself yet. I'm just going to pause this video again now. So in this question, you asked about the enthalpy change of combustion of ethine, which would give you carbon dioxide and water. But in the question, you're asked about, or you're told about, the enthalpy change of formation of ethine, which comes from 2 carbons and 1 hydrogen molecule, right? I've not given a value for oxygen to oxygen because that's 0, of course. And you're also given the enthalpy changes of combustion of carbon and hydrogen, which I've put here. When you put that together, the clockwise arrows are this one and this one. Anti-clockwise arrows this one. And you rearrange, you end up with this. And I get, and other people in here get minus 1302. And these questions are not straightforward, but who got that far and managed to get anyone get the right answer? A few of you. If you were slipped up on that, it's not the end of the world. That is difficult. Right, so I'm going to stop the video there. I'm going to go to slides. I'm going to share the slides, which are, for the sake of the people not here, energetics less than 6. And we're going to go to the slides now and look at from slide 14 onwards, 14, 15 onwards.